Hello friends, I'm going to explain the details about the document titled as NASA-SP-8007. This document is about the empirical relations for buckling of thin-walled circular cylinders. So it covers both the metallic as well as composite cylinder, as well as stiffened monocoque cylinder. So different varieties of cylinders which come under the category of thin-walled circular cylinder has been covered as a part of this document. So basically, it tries to accurately capture the buckling load of a particular cylinder subject to axial compression, external pressure, torsion, different kind of loading. This document is almost 107, 109 pages. So it's a elaborate document which covers a lot of things. But we are not going to discuss the complete things of out of it. Rather, we are only going to focus on the composite part of it. So if we see this first revision of this document was published in somewhere around 1968. But in this video, we are going to talk about the orthotropic cylinders, which is orthotropic means the cylinder which are made up of composite material. So when we go to section 4.1.2, we come to the details of that. So which is subjected to among the so the material is fixed that we have already told that it is the thin cylinder is going to be made up of composite, but and the loading also can be different type which can cause the buckling. One is torsion can cause buckling, one is external pressure can cause buckling, and external axial compression can also cause buckling. So now in this video we are covering axial compression, but the other forms of load are also similar. Once this part is clear, the other part will be similar. It can be easily made, but in case of that is required from me, it can be commented so that it will then I'll make then I will come to know that interest my audience want that particular video. So based on that feedback, I will make a video on that also. But in this video, we are going to talk about axial compression load only, which is applied for a orthotropic cylinder. That is the cylinder made of a composite material, and to find out accurately when at what load the cylinder is going to buckle. So as I mentioned a while ago, that this document was originally published in 1968 also. So this is the latest version of 2020. So where this is the formula where NX represents the load per unit length in the axial direction, which will cause buckling. For the This is the equation 52. So there are various parameters. A11, A matrix is there. L is the length. M and N are the different number which is explained in this document. That number of half axial waves, circumferential full waves, all those things. And then pi is okay, pi every one of us know. L okay, then anything else to be explained. So this is how the equation, first equation, the main equation, which tells us the load at which it will buckle. But then this same thing is this equation 52 and 53 are one and the same. They're just expanded. But then equation 53 is expanded. What are the each component of this equation 53 is explained from 54 to 59. A11, A22, A33, everything is explained. And then these equations, these A components uses E, G, D, C, K. Now this is not very clearly what I found from my observation, that these quantities are not very clearly explained in this document. I had to do a little bit of research to accurately pinpoint what does this actually mean for a composite cylinder which is not stiffened by any external stiffener. Then what does this quantity actually mean? How to calculate them? And so these are the things which I had to refer to few documents which I'll be explaining in this video as also. So then the next part is a knockdown factor is also given explicitly how to calculate the knockdown. So the knockdown factor is a quantity which we have to multiply with a linear buckling analysis to get a value closer to the experimental loading. So knockdown factor is kind of an efficiency. It's like when we calculate the linear buckling analysis, we get the overestimated load, but the actual cylinder will fail at a lesser load because actual cylinder will have so many discontinuities and so many defects, undulations. All those things will contribute to a lesser buckling load. So those factors are accounted in knockdown factor, and the good part is that this is also can be calculated, roughly calculated by a relation which is given by equation number 60. So equation number 60 uses a term called phi, which is again calculated by equation number 61 given in this. So after this, again, there are some other condition. If it is subjected to bending, there are few more changes in the equation. And if it is external pressure, then the expression changes a little bit. So these are not very difficult to calculate. If it is torsion, also again the expression changes. But I am explaining about the axial compression alone. The other things can be explained in future videos if required. I suppose that it will not be required because the fundamental parts I'll be covering in this video, which will enable everyone to make the other parts by themselves. Now, what is the other terms which were used? EX, EY, EXY, GXY, DX. All these things I have already written in the form of a red font in this PDF. That E represents the quantities which are taken from A matrix. D represents or directly from D matrix of the composite, and the C quantity with C with some subscript are the one which is taken from D matrix. So now what is A, B, and D matrix is something which is very fundamental to composite material, and the calculation of these quantities have also been explained in one of my previous videos, and I will put a link to that in the description also. So these quantities A, D, and B are to be calculated from from the uh, explanation which I gave earlier. Now this video will also contain that. I'll be explaining and by going to MATLAB how to calculate all these quantities also, but not in detail because it has been covered in the previous video already. Now what I'll be focusing more in this video is there is a document. Okay, why? Okay, first I'll explain why it is A, D, and this B matrix. How I came to know this entire document of NASA ASP8007 has been developed from the work of a person called Robert M. Johns. So he has written so many papers in those times, and based on that, he used to have B matrix as a extensional stiffness matrix for the layered shell. So basically, in-plane stiffness was represented, as we know that in-plane stiffness is represented by A matrix. He used to represent A matrix for some other purpose, so that is why he used B for in-plane extension, C for the coupling. But we know that D matrix represents the coupling. D matrix for the bending stiffness, as in the present convention, also D matrix represent the bending stiffness. So this is the convention which he has explained here in this paper, which made me to use it. And now this second part of this equations everywhere, these are due to the stiffness. So we have, while coding, since we are going to consider monocoque composite cylinder, we'll be ignoring these parts which are like S subscript means stiffness, R I think some radial or rib or something. I have to go through again. This is the work which I've done long ago, maybe 1 or 2 years ago, more than 2 years ago. So that is the reason I'm not okay. This subscript has to be relooked. So now the second thing I want to tell, this ABD matrix, how it has come, the source has been explained. Second thing is regarding the previous document. The previous document, if we see, this section is also there, orthotropic cylinder, then axial compression is the first loading type it was explained. Everything, but 99% of things are same, but except for few things. That is, one is this equation. The equation number 44, you will not find this equation in the new version of it. So many veterans I have seen and many seniors, what they do is they use this equation because the other paper came on 2020 only, and this paper is written little confusing manner, and that is the reason, because to avoid the confusion, this equation is removed in the latest version. So this equation already gamma is used, which is the knockdown factor, and beta is one more factor, which is I think somewhere it is explained in this paper. So which gives a value of nx. If even if we use this value, it is not wrong, but we have to just take into account that whatever nx we are going to calculate it through equation number 44 is already accounting the knockdown factor. Viewers, please mind it that if you are using, in case you have a code which uses equation number 44, please do not multiply the knockdown factor after calculating next again, because it is already considering the knockdown factor. So that is what I wanted to highlight about. After that, this bending, torsion, extension, stiffness, everything is same as per the latest version. So we'll close this file and let this file be open, and the other files can be closed. Now we'll go straight to the code where CLC to clear, clear all. So now everything has been cleared. Now this is the code which calculates first from here to I'll just tell from 62, line number 62, from line 1 to line 62 are actually a part of the previous calculation which I have explained in my previous video about the calculation of ABD matrix for a particular laminate. This is exactly the same, which uses one Excel sheet. This Excel sheet, we have to define the number of layers, what are the properties of each layer, the angle of each layer, thickness of each layer, which calculates the ABD matrices. Now, these are two results which I have calculated based on the old paper, 1968 paper and 2020 paper. There are slightly different formulations given, and I have coded both the formulations to compare the results. So the values of material that I've used is a generic property which I think I took it from the ANSYS handbook, and the angles and other things. Okay, let me see the angles. Angle, I think I've just randomly given plus minus 15 for all the things, but it can be any value in degree. So coming to the thing, the trans is another file which will be called somewhere for transposing, like q bar na, for transposing, that we need some function that has also been explained earlier in the previous video. So now, after calculating the ABD matrix, the main content starts for this video. That is how to calculate the values of m and n. The values of m and n are to be determined in such a way that they give the minimum buckling load. L is the length for a particular cylinder. I consider 5 meter length, and 2 meter 2 meter as the radius. In this case, say we will change this value to 4 meter length, and say uh, 1500 1500, that is 3 meter diameter, 3 meter diameter, 4 meter length. So suppose this is the external dimension of this. And now this main thing is how these values are calculated. Like as I was mentioning, that Ex, Ey, Exy, and Gxy are the impedance differences, so which are taken from the A matrix. Then D matrix is D matrix. There is no confusion about that. C matrix is actually B matrix, and one value Kxy is also from B matrix. Now, if LC, like that is the lowest that is critical load for one means method one, and two means method two. Four, since I have calculated both as per the first formula, this is we have to do one nested for loop has to be run with the formulas which are given in both the papers in the beginning. So those formulas, if I do and calculate the values of LC1 for each value of m and n, and among each value of m and n, if I have to take the minimum, that part is done subsequently. But then this LC1 is made as a matrix, and all the values for different combination of m and n are filled inside it. Similarly, the LC2 is again a matrix which contains all the values for the second formula. So the second formula, okay, this first formula is as per the first formula is as per the new document. Sorry, the second formula is as per the old document, which which already contains that. So we should not multiply that. We should not multiply the lockdown factor after that. Anyways, so coming to that, and after that we have plotted the value of the buckling load as a function at both m and n, and then okay, this some basic things we have printed, and then we have given the values of the okay, then if we see that LC1, because which represented the new formula, there only we have multiplied the gamma, which is the knockdown factor. But for the LC2, we have not multiplied any knockdown factor because it's already containing the gamma inside it. So we have, this is the factor thing, main thing which I was trying to focus, which I was trying to recruit, that this should not be done, that gamma should be multiplied in both the cases, which has been done by many. It will be a wrong thing. Then if we run this code, within few seconds, okay, let us see why it is not running, because this file is open. I just do one thing. If I want, I can delete everything also. All the things, ABD matrix will be recalculated. Even if I'm not deleting also, it will be recalculated. That's not a big problem. So I'll just rerun it. So within few seconds, it will run that. Some things we have plotted, and these things have come out. These are not mandatory for the calculation of critical buckling load. I'll go to the folder where it was done. I think this is the folder. Um, yeah, this is the folder, and we see that these two loads are pretty close, 35 kilonewton and 568 kilonewton. So these are around 5 to 6% different. Difference is about 5 to 6%, but then they are pretty close, and this is lower. The new load is lower, and it is more conservative, and it is, I mean, what I mean to say is they are close, and the new one is more conservative. So this is how we have to calculate, and since it is symmetric, so this B matrix is 0. All those things are done. So now this can be correlated with any research paper. This correlation with research paper, I have not planned today. We can do that in some other video. And for the time being, thank you for watching, and let me know what other topics should I cover, and please increase engagement in my video. Earlier I was not talking about that, to either to like or subscribe, but now I would like to request, because some kind of encouragement is required to keep ourselves making the video, sharing the knowledge. I make videos primarily to compile my works which I have done so that it will be serving as a reference for myself also in future. At the same time, I want people also to get benefited from it. So for that, I need something in return, which everybody asks, but I'm also asking, please give your support to it by subscribing and liking and commenting. Thank you for watching the video.